Welcome to the second part of an examination of why scientists are so convinced that human actions are driving climate change. My goal here is to explain the underlying science clearly and accurately, avoiding both oversimplification and emotional appeals. This approach differs somewhat from certain elements in Al Gore's film, An Inconvenient Truth, particularly the dramatic animated scene depicting a polar bear seemingly on the verge of drowning due to melting ice. While Gore's film succeeded in raising public awareness about climate change, some of its scientific portrayals were, at times, debatable. This led some viewers to question the overall scientific validity of the message presented. Ultimately, to think like a physicist isn't about solving complex equations. Instead, it's about adopting a mindset rooted in curiosity, critical thinking, and evidence-based reasoning. This means that when we're trying to answer big questions like what causes climate change, it's crucial to seek out reliable data and form conclusions based on what the evidence strongly suggests, rather than relying on gut feelings or personal biases. Have you ever wondered why we have different seasons throughout the year? It all comes down to Earth's tilt. Our planet isn't sitting straight up and down. Instead, its axis, the imaginary line it spins on, is tilted about 23.5 degrees relative to its path around the sun. This tilt stays pretty much the same as Earth makes its yearly orbit. Here's how that tilt creates our seasons. When the northern hemisphere is tilted towards the sun, it gets more direct sunlight. Think of it like shining a flashlight straight onto a surface. The light is concentrated and strong. That means the sun appears higher in the sky, and we experience longer days. All these factors together bring us summer in the northern hemisphere. At the same time, the southern hemisphere is tilted away from the sun, getting less direct light and shorter days, which means it's having winter. As Earth continues its orbit, there are also times when neither hemisphere is tilted significantly towards or away from the sun. These periods are called equinoxes, and they mark the beginning of spring and autumn, or fall. During an equinox, both halves of the world get roughly equal amounts of direct sunlight, and day and night are pretty much the same length everywhere. These are like the transition periods between the warm summer and cold winter. Around 6 months after the summer, as Earth keeps moving around the sun, the northern hemisphere starts to tilt away. This means the sun appears lower in the sky, and its light hits at more of a slant, spreading out the heat over a bigger area. Plus, there are fewer hours of daylight. All these things combine to make it colder, bringing on winter in the northern hemisphere. At the exact same time, the southern hemisphere is tilted towards the sun, so they're having their summer. When we think about seasons, many people assume Earth's distance from the sun is the main reason for hot summers and cold winters. But actually, that's not quite right. While our planet's orbit isn't a perfect circle, the slight change in distance from the sun has a super minor effect on the seasons. The real game changer is the tilt of Earth's axis. This tilt determines which parts of the planet get more direct sunlight throughout the year, causing those seasonal changes. So, when the northern hemisphere is tilted away from the sun, it experiences colder temperatures and winter, while the southern hemisphere, tilted towards the sun, enjoys summer. This same axial tilt, along with other subtle changes in Earth's orbit over thousands of years, are what we call Milankovitch cycles, and they're what really influence long-term climate shifts, even leading to ice ages. Alright, so the Milankovitch theory is basically this idea that explains huge climate changes over super long periods, like why we have ice ages and then warmer periods. It all comes down to how Earth moves around the sun, specifically 3 main things that happen very, very slowly. First, there's eccentricity, which is about how stretched out or circular Earth's orbit is. Imagine Earth's path around the sun like an oval that sometimes gets more squished and sometimes more round over about 100,000 years. When it's more squished, there's a bigger difference in how much sunlight different parts of Earth get, making seasons more extreme in one hemisphere and milder in the other. Then we have obliquity, or the tilt of Earth's axis. Our planet isn't straight up and down. It's currently tilted at about 23.5 degrees. This tilt actually changes slightly over about 41,000 years, wobbling between 22.1 and 24.5 degrees. A bigger tilt means more intense seasons, hotter summers, colder winters, while a smaller tilt means milder seasons. Interestingly, a smaller tilt can actually help ice sheets grow because cooler summers in the polar regions mean less snow and ice melt away. Finally, there's precession, which is like Earth's axis wobbling like a spinning top, completing a full circle every 26,000 years. This wobble changes when certain seasons happen in relation to Earth's position closest to or farthest from the sun. For example, right now, the northern hemisphere has winter when we're closest to the sun. Precession shifts this timing, which affect how strong the seasons are in each hemisphere over long stretches of time. Physics tells us that ice ages happen when these 3 cycles line up in a way that means the northern hemisphere's high latitudes don't get as much sunlight in the summer. The northern hemisphere is key here because it has big land areas where those massive ice sheets can really expand. Note, in figure 8.10, the relative peak summer solar intensity at 65 degrees north over 800,000 years shows a decreasing trend at the present time, which implies the Earth should be cooling down. When summer sunlight isn't as strong in the northern parts of the world, due to a mix of Earth's tilt, wobble, and orbit, the snow that falls in winter doesn't completely melt. Over thousands of years, this allows snow and ice to build up, eventually forming huge ice sheets. These growing ice sheets actually make things even colder because ice is super reflective, bouncing sunlight back into space. This positive feedback loop then leads to even more ice growth. Plus, changes in carbon dioxide in the air, often connected to how warm the oceans are and what living things are doing, can also crank up or cool down these temperature shifts. You know how the sun's gravity keeps Earth in orbit? Well, while the sun is definitely in charge, Jupiter, our solar system's biggest planet, also plays a pretty big role. Jupiter's huge gravitational pull actually tugs on Earth, subtly changing the shape of our orbit over really long periods. We're talking tens to hundreds of thousands of years. These slight changes, driven by Jupiter, affect how much sunlight reaches different parts of Earth at different times, which then influences long-term climate patterns and even kicks off ice ages. This whole idea is a big part of something called the Milankovitch theory. Imagine you have three random objects floating in space, all pulling on each other with their gravity. Even though they're all moving, there's one special point called the center of mass that acts like the balancing point for the whole system. If you could push this entire group of objects right at that center of mass, the whole thing would just move in a straight line without spinning. If you pushed it anywhere else, it would start to tumble. The cool thing is, even with all the internal tugging from gravity between the objects, this center of mass keeps moving in a straight line at a steady speed unless something from outside the system pushes or pulls on it. Now, think about trying to balance yourself. Your body, with all its different parts like your head, arms, and legs, also has a center of mass, usually somewhere around your belly button. When you're standing still, this center of mass is directly above your feet, which is your base of support. Gravity is pulling your center of mass down, but the ground is pushing up through your feet, keeping everything stable. But when your center of mass shifts outside, or even close to the edge of your feet, that's when balancing gets tricky. Here's why. Gravity still pulls your center of mass down, but now it creates a rotational force, or torque, trying to tip you over. It's like a seesaw. The further your center of mass moves from being directly over your feet, the stronger that tipping force becomes. To avoid falling, your body has to quickly move and adjust, engaging muscles to shift your weight and bring your center of mass back over your feet. That's why it's so much harder to balance when you're leaning way forward, standing on one leg, or carrying something heavy that throws off your balance. Your body has to work much harder to keep that center of mass in line. Imagine an ice skater doing a spin. They start with their arms and maybe a leg stretched out, right? When they do that, their body mass is spread out pretty far from the center they're spinning around. But here's the cool part. When they pull their arms and leg in tight to their body, they actually reduce something called their moment of inertia. Think of moment of inertia as how much an object resists spinning faster or slower. Now, there's a physics rule called conservation of angular momentum. Basically, if nothing else is messing with their spin, like friction from the ice, the skater's spinning power stays the same. So, when they reduce their moment of inertia by pulling in their limbs, that spinning power has to go somewhere. To keep it constant, they have to spin faster. It's like their body automatically speeds up to make up for the change. And when they want to slow down, they just stick their arms and legs back out, increasing their moment of inertia again, which makes them spin slower. A simple, analogous spinning physics experiment that illustrates the complex interplay in the Milankovitch cycles involves taking a small book and securing it with a rubber band so it won't open when tossed. If you spin around its shortest side, like flipping it end over end, or its longest side, like spinning it horizontally, it'll usually rotate pretty smoothly. But try tossing it so it spins around its middle axis, and you'll notice something weird. It'll tumble and flip in an unpredictable way. This oddness of the tumbling book is a bit like how the Milankovitch cycles work, even though it's not the exact same kind of instability. It helps us understand the complex and sometimes unpredictable way three different cycles of Earth's orbit and tilt combine to affect our climate. Eccentricity, orbital shape, how stretched out or circular Earth's path around the sun is changing roughly every 100,000 years. Obliquity, axial tilt, how much Earth's axis is tilted, which varies approximately every 41,000 years. Precession, axial wobble, the slight wobble of Earth's axis, completing a cycle about every 26,000 years. Just as the book's middle axis creates an unstable tumble where energy shifts around, the Milankovitch cycles show how these three astronomical factors, with their different timescales, interact in a non-uniform way to influence Earth's climate over thousands of years. It's not a physical tumbling, but a complex interplay that leads to significant climate variations, like ice ages, climate models, and the butterfly effect. Imagine trying to predict the exact path of 3 billiard balls bouncing around on a table for an hour. It gets super complicated, right? That's kind of what climate change modeling is like, and it's similar to a famous physics problem called the three-body problem. Both are described as somewhat predictably chaotic because of something called sensitive dependence on initial conditions, or the butterfly effect. Here's why. In simple systems, like just two planets orbiting each other, their movements are easy to predict. But at a third body, and suddenly all three are tugging on each other in constantly changing ways. There's no single math equation to perfectly predict where they'll be way in the future. Even a tiny, unmeasurable change in where they start could lead to completely different outcomes down the line. For example, a tiny change in a climate model's starting temperature could lead to vastly different long-term predictions for sea level rise. However, it's somewhat predictably chaotic because a physicist can make pretty good predictions for shorter periods. Those tiny differences take time to snowball into major changes. Since we can't get an exact answer, scientists use powerful computers to run simulations, taking small steps to approximate the movements. But because even tiny rounding errors can get massively amplified over time, these long-term predictions can still vary a lot. So, while we can't pinpoint every single detail of the climate's future decades from now, we can still understand its general trends and predict what might happen in the near future. When scientists try to figure out if humans are causing climate change, it's pretty similar to a court trial. The whole scientific community acts like the court, gathering tons of evidence. They collect data on everything from current carbon dioxide levels in the air to ancient air trapped in ice, showing how much carbon dioxide was around way back when. They also track rising global temperatures, melting glaciers, and higher sea levels. They even compare today's warming to what Earth's natural cycles, like Milankovitch cycles, suggest should be happening. Based on all this, they form a hypothesis like burning fossil fuels is making Earth warmer, and then make predictions about what we should see if that's true. After that, their work goes through a super tough cross-examination called peer review and replication. This is where other scientists pick apart their data, methods, and conclusions, trying to find any mistakes or better explanations. If the evidence holds up to all this scrutiny from thousands of experts over many years, it gets a lot stronger. Finally, they reach a scientific consensus, which is like the verdict. It's not based on just one piece of evidence, but a massive amount of consistent data, all pointing to the same conclusion. For climate change, the overwhelming scientific consensus is that human activities are definitely the main cause of the warming we're seeing. It's like having so much undeniable proof against someone that you just know they're guilty. The scientific argument for human-caused climate change is primarily based on several key pieces of evidence. Direct measurements of greenhouse gas increases. For decades, measurements from around the world have shown a significant and continuous rise in the concentration of carbon dioxide and other greenhouse gases in the atmosphere since the start of the Industrial Revolution. Historical atmospheric composition from ice cores. Analysis of air trapped in ice cores from Greenland and Antarctica provides a historical record of atmospheric composition. This record reveals that current greenhouse gas levels are unprecedented in at least the last 800,000 years, with the rapid increase coinciding with the start of industrialization. Milankovitch cycles versus observed trends. Based on Milankovitch cycle data, Earth should actually be very slowly cooling down because solar intensity is gradually decreasing. This directly contradicts the warming trend we're currently observing. Observed warming patterns. The patterns of warming observed across the globe are consistent with the effects of increased greenhouse gases. The bottom line is that both kids and adults should be asking why the highest point in the Arctic just experienced rain for the first time, why temperatures of 67 degrees Fahrenheit were observed in Alaska during December, and why growing numbers of flowers have been observed in Antarctica over the past decade. The fact is, the only explanation for these unusual warming trends in the Arctic and Antarctic regions is the scientifically measured, ever-increasing concentrations of greenhouse gases, as shown by data like the Keeling curve. A closing thought. Sea level rise is a significant and inevitable consequence of these unusual warming trends, primarily driven by two main factors: thermal expansion of seawater and the melting of land-based ice, such as glaciers and ice sheets. If these unusual warming trends continue, coastal areas all around the world will be flooded. This in turn raises questions of how soon and how high global flooding will be. It's challenging to give a precise timeline for human-caused climate change to manifest on a biblical scale, primarily because biblical scale events, like the Genesis flood, are often described as sudden, widespread, and divinely orchestrated, making direct scientific comparison difficult. Basically, If current global warming trends continue and nothing is done to significantly reduce greenhouse gas emissions, leading to high levels of warming, for example, a peak of 5 degrees Celsius or more above pre-industrial levels, the mean global sea level rise over the next 2,000 years, which the average person on the street would say is a long time, but in geological time is a proverbial blink of an eye, could be 19 to 22 meters, approximately 62 to 72 feet, and potentially even as high as 28 to 37 meters, 92 to 121.5 feet.